We present K-planes, a general method for efficiently representing and optimizing radiance fields for static scenes, dynamic scenes, and scenes with varying appearance. More generally, K-planes can be used to represent a scene in arbitrary dimensions, using far less memory than a direct voxel representation while maintaining aspects of interpretability. Concretely, we represent a d-dimensional space using k equals d choose 2 two-dimensional planes, representing interactions between every unique pair of coordinates. We use planes as our basic model component because they lend themselves well to interpretability, providing clear geometric correspondences, and can be represented directly at high resolution. For a 3D space, such as a static scene, our model uses 3 planes representing xy, xz, and yz. For a 4D space, such as a dynamic scene, our model uses 6 planes, including the 3 spatial planes and 3 space-time planes, xt, yt, and zt. To render a ray, we trace it through the scene and sample points along it, prioritizing points near object surfaces. We project the coordinates of the point into each plane, for example here the xy, xz, and yz planes, and retrieve the feature values inside each plane using bilinear interpolation. We multiply features from each plane together to produce a single feature vector. We repeat the process at multiple scales and concatenate the resulting feature vectors. If the scene is dynamic, we do the same in all 6 planes, including the xt, yt, and zt planes. This feature vector can then be decoded using either a lightweight MLP in our hybrid model or a linear decoder in our explicit model. In either case, the decoder maps our localized feature vector f into a density value sigma, and maps the feature and view direction d into RGB color. Our hybrid decoder uses 2 lightweight MLPs, one in purple that maps features f into density sigma and auxiliary features f hat, and another in red that maps these auxiliary features and the view direction d into RGB color. Our explicit decoder is instead based on dot products of the features f with learned basis functions for density and view-dependent color. We learn a basis vector b sigma in purple for density and a basis function brgb in red for view-dependent color. The color basis is implemented as a lightweight MLP that maps view direction into a basis vector, whose dot product with the features f determines the RGB color. Here's an example reconstruction of a dynamic scene, where we can move the camera while the cook cooks. We can use either decoder and get similar results. This shows that the planar representation really captures the information of the scene, and it's not relying too much on a nonlinear decoder. K-planes optimizes on a 10-second video in about 2 hours on a single GPU, whereas the prior state-of-the-art method dynerf trains for a week across 8 GPUs. K-planes also reaches similar reconstruction quality metrics compared to dynerf, without excessive memory footprint. Since the K-plane's representation is comprised of space-only and space-time planes, we can decompose a scene into static and dynamic parts. We render the static part by setting the time plane features to 1, the multiplicative identity. Then the residual between the full rendering and the static rendering reveals the dynamic part of the scene. We can even visualize the motion directly through the space-time planes of the model. Here we show the xt plane, where the motion of the cook's 2 hands is clearly visible across time. The K-plane's separation of dimensions into different planes also enables dimension-specific priors and regularization, such as sparse edges across space and minimal acceleration over time. The left panel shows our reconstruction of the bouncing balls scene from dynerf from a fixed camera viewpoint. The middle panel illustrates total variation over the spatial dimensions of this video, in which edges appear bright. We regularize the total variation of the spatial dimensions of each of our feature planes to encourage coherent objects when training from limited viewpoints. The right panel illustrates our temporal regularizer, in which dynamic regions appear bright. We regularize the second derivative or acceleration of the features along the time dimension of each plane to encourage smooth motion. Because we use separate feature decoders for density and color, we can learn consistent geometry even under changing illumination. These models were trained using tourist photographs taken at different times of day, and then rendered with a moving camera while interpolating between different appearances. We conclude with some additional results using K-planes to optimize dynamic scenes from the dynerf and dnerf datasets, and static scenes from the LLFF and nerf datasets. Thanks for watching.